My name is Dean DeHaven. I'm Chief Executive Officer of a new startup company called Cambridge Quantum Solutions. And I'm going to read three overviews of the patent process, the actual patent draft itself, which I did myself in Word in a 2-column format required by the U.S. government. I have a set of schematics that goes with this included, and it includes about 30 diagrams in the normal 11 by 17 inch engineering drawings, of which all of it is proprietary stuff. And we have a technology demonstrator, which is a machine that actually is the demonstratable model. Okay, now, as I said, 3 sections, and I'll just read them. Okay, section 1 is the data sheet for the patent process, and the title of this is Cambridge Quantum Solutions Electromagnetic Processor. Owner, Cambridge Quantum Solutions, LLC, Cambridge, Massachusetts. Inventor, Dean DeHaven, me, and Cambridge, Massachusetts. And the original document date was January the 11th, 2016. But we have a current version of that, of the document as we proceed further. Okay, section 1 is down. This is the federal government's U.S. Patent Office format. The abstract 1.100, Cambridge Quantum Solutions, LLC, has been involved in the development of a quantum mechanical machine theory that does not use digital computers to simulate known quantum processes. The CQS processor project began with an idea based on the components intrinsic to the beryllium atom. This atom exists in nature for an instant with a symmetric number of 4 protons and 4 neutrons, but an extra neutron appears in the nucleus in its stable state. However, the CQS global system structure is based on 4 protons, 4 neutrons, and 2 spherical electron orbital shells. Paragraph 1.101 on the data sheet, the model reference system concept. The CQS electromagnetic processor is based on a model reference system concept, which proposes a system design process where the central advantage for both the theoretical model and the future physical system in production involve the same performance parameters. The goal is to minimize the difference between the model and the production versions. The central advantage involves a functional description of the CQS's machine cycle in section 3 of 3 that proposes a new type of electromagnetic processor that processes optical electromagnetic packets as the atom does. Physics involves making repeatable observations and quantitative measurements that support and or validate the theoretical model. The goal for the model is to predict what the machine will do when built according to the proposed theory. If a model is considered risky, it means that it might not work as described. If the model fails to meet the predictions when measurements and results are formulated, it does not represent a valid theory, and it must be abandoned or modified. If the model passes its empirical test, then perhaps it can be considered a viable theory. This defines what is meant by the term model reference system. That's overview of the data sheet, section 1. Section 2, 2.100, introduction to section 2. The CQS electromagnetic processor concept is based on the following premise. Nature's own electromagnetic processor is the atom. Therefore, the CQS processor must be based in quantum theory. In order to present this concept in a moderately sized document, much of the theory must be left out, as the goal here is to explain in section 3 of 3 the CQS processor machine theory, which constitutes the main advantage. The focus in section 2 will remain on 2 system models, which makes liberal use of technical information gathered from the reference sources. Model number 1, the classical linear time invariant model, and 2, the hydrogen Coulomb atomic model. The technical information has been carefully transcribed, edited, and paraphrased into Section 2 of this document with the following goal: to perform a unified general analysis of what constitutes a systematic approach involving 3 tasks any machine or processor must include: input, process, output. The term classical physics, as used here, refers to the physics before the advent of quantum mechanics. Classical physics includes Newton's equations for motion of particles, the Maxwell-Faraday theory of electromagnetic fields, and Einstein's general theory of relativity. But it is more than just specific theories of specific phenomena. It is a set of principles and rules, an underlying logic that governs all phenomena, for which the quantum uncertainty is not important. Those general rules are called classical mechanics. That's the end of what I'm going to read in Section 2 overview and Section 3 of 3. And this is 3/100, paragraph, Introduction to Section 3. The CQS processor machine theory will be presented in this last section. Section 2 involved a general mathematical description of 2 types of systems. 1, the linear time invariant LTI system. The LTI model is a classical system that is completely deterministic. The mathematical description was relatively simple, involving 14 equations or so. And model number 2, the hydrogen Coulomb atomic system. This model involves a general overview of the hydrogen Coulomb atomic model with around 200 equations and about a dozen diagrams. This model, this model presents a quantum mechanical system based on probability. The analysis left out most of the quantum mechanical formalism, such as spin, relativity theory, etc., in order to describe the quantum mechanical system concept with a minimum amount of mathematical theory. The problem with any quantum mechanical system is that the particles cannot be directly observed in terms of classical position and momentum. For example, a mathematical space called the Hilbert space, or called Hilbert space, is needed that assigns operators for these and many other observables. In the end, only a statistical projection operator will describe the observable within the constraints of the Heisenberg uncertainty principle and quantum mechanics. This means it is not possible to measure a particle's position and momentum in a well-defined manner simultaneously, as is easily done in any classical system. Paragraph 3/101, the CQS system model will make use of what we proprietarily call the dot shell object context, or DSO. And let's see, as the 2 models in Section 2 used as well. There will be a geometric analysis involving certain well-known constants such as pi, square root of 2, and the natural logarithmic number called e. This analysis will focus on how these mathematical constants are to be interpreted within a non-standard coordinate system called T-symmetry. T-symmetry is based on 300 radial degrees and 50 concentric rings in the 2-dimensional context and 50 concentric shells in the 3-dimensional context. A system structure called JK symmetry after Johannes Kepler will be presented, involving the 5 so-called perfect solids, an octahedron, tetrahedron, cube, dodecahedron, and the icosahedron. Each of the 5 structures represent an internal functional component which is inscribed into the spherical boundary shell of the DSO context in a certain order. The cube, for example, will involve a system structure called E-symmetry, which contains 216 space cells called Eston qubits. The three symmetries, T, JK, and E, form the CQS machine's global internal structure. And in the last paragraph, 3.102, a high-level algorithm called XMF will be presented, which involves a separate hybrid electronic platform called a technology demonstrator, which I was showing the patent 11x17 schematics. The XMF involves four machine states for the CQS machine cycle: absorption, a dual internal state called isolation formulation, and emission. The reference to the atomic system model is intentional with the machine state names. A unique concept will be presented involving what are called pathways. Pathways involve the decimal expansions of a few constants mentioned and how they work to support an actual system model for an electromagnetic machine. The central advantage will present the argument that CQS machine cycle theory proposes a general model for the beryllium atom particularly. That's it. Thank you very much for listening to this. My name again is Dean DeHaven, Chief Executive Officer for Cambridge Quantum Solutions, and I thank you for listening, and we'll take it from here.